everybody. So this is going to be a video on sort of rate of change, computing average rate of change given a few different ways that it might be represented. Please focus. Please focus. And also behavior of graphs. So we'll start with rate of change. Average rate of change of a function, we'll call it f, over some interval, the interval from a to b, is given by this formula: f of b minus f of a over b minus a. So you're given some function f, however it's given to you as actual, like the equation of the function. Maybe you're given a graph, maybe you're given a table of values, and you're asked to find the average rate of change over some interval from a to b. So that average rate of change is f of b minus f of a divided by b minus a. Does that look familiar to you? It might. Let me rewrite it in a slightly different way that's actually equivalent, but maybe is a little bit more familiar to you. What if I wrote it as y2 minus y1 over x2 minus x1? Do you remember that? Do you remember what that is? This is the standard formula for slope, which is applied to linear equations. And it's the exact same idea, it's just that now we don't require the equation to be linear. It could be some very curvy equation, and we can still compute the average rate of change. So let's do that. Let's do it in a few different ways. First, we'll do it by computing the average rate of change, assuming that maybe we're given like the equation of the function. So suppose that we have the function f of x equals, I don't know, what's a fun one? X cubed minus 2. I don't know. I'm just coming up with something off the top of my head. And let's choose an interval. We'll do the interval from, what might be good? I'm trying to make sure I don't give myself numbers that are going to be tough to compute. Let's do from -1 to 4. I can do 4 cubed. Okay, so if we want to find the average rate of change of f of x equals x cubed minus 2 on the interval from -1 to 4, well, what are the pieces that we're going to need? Let's just first rewrite the formula using like our new function. So, and we're still going to write it as in function notation. So we're looking at f of b, which is b is 4, so we want to find f of 4 minus f of -1 divided by 4 minus -1. Right? We're just plugging things into our original formula. All right, well, before we can really crunch this thing out, we need to know what is f of 4, and we need to know what is f of -1. So let's calculate that. F of 4 means take 4 and plug it in for x. So we need to calculate what is 4 cubed minus 2. Well, 4 cubed, 4 squared is 16. 16 times 4 is 64. So 64 minus 2 is 62. And the same thing for f of -1. We need -1 cubed minus 2. Be careful, what is -1 cubed? Take a second, pause the video, figure it out. What's -1 cubed? Turns out, -1 cubed is just -1. So this is -1 minus 2, or -3. Great. We have values for f of 4 and f of -1, so let's plug those in. F of 4 was 62, so we're looking at 62 minus -3 divided by 4. So in the numerator here, 4 minus -1, that's the same as 4 plus 1. So 62, same thing up here. 62 minus -3 is really 62 plus 3, so 65 over 5. And surely that is divisible by 5. What is it, 13? Yeah, 13. That's the average rate of change. And what does that really kind of mean, by the way? I'll show you what it means. I think that it makes a little bit more sense to graph it. I guess I'll say it first. 13, this is the slope between these 2 points. The 2 points, -1, or I guess I should say f of -1 and f of 4. So if you were to sort of plot out those points, and here's kind of what x cubed minus 2 is going to look like. Something like that. So f of -1 is like right here at -3. F of 4 is way off the charts. It's like way up here, way up there. But if we were to plot those and then say that we drew a line between them, just a straight line like that, then, and maybe I can even, maybe I can even make it in a different color. That's kind of fun. And if we drew this straight line and then we asked, what is the slope of the line that connects these 2 points? Well, that slope is what we just found. The slope of that line, oh, my pen doesn't work. Come on. It stopped working. This was a really good pen. Come on. It was working just the other day. I graded things with it. What's going on? What's happening in my life? The slope of this line, in any case, is 13. That's what we're looking at. That's what we just calculated. Does this one work? None of my pens work. Why not? I don't know. Who did that? Which one of you did that? So that's what the average rate of change is. It's just saying, all right, imagine that we have a function. We pick out 2 points on that function. We draw a line between them. What's the slope of that line? Average rate of change. So this is maybe a hint. How would you solve average rate of change if instead of given an equation, maybe you're given a graph? So something like, let's see, and since it's going to be a graph, we can kind of do whatever we want. Whatever this really funky equation ends up being. Something like that. And suppose that we are able to pick out 2 points. So like maybe we're given this graph and we're asked, what is the average rate of change from, like, what might that be, -4 to, we'll pick another point over here, 7. I don't know. I'm just making things up. So imagine that this is, so here's -4, here's 7, and maybe this is the point 7 comma, maybe it's like a crazy y scale, 7 comma 10. This point right here is the point 4 comma 23. I don't know, something strange. I'm just trying to pick up some strange numbers. Man, I wish my pens would work. That would be great. Surely whenever I stop this video, the pens will magically start working again. So if we were to draw a line through these points, the average rate of change of this graph or of this equation from over the interval from -4 to 7 is just the slope of this line. So again, it's the same equation, f of 7 minus f of -4 divided by 7 minus -4. Except this time, we're given a graph. We're basically told what the values of f of 7 and f of -4 are, rather than us having to compute them ourselves. So f of 7 is 10. F of 7 is equal to 10. F of -4 is equal to 23. All of that is divided by 7 plus 4 is 11. So 10 minus 23 is -13. -13 over 11. That's the average rate of change of this equation over the interval -4 to 7. That's it. It's just the slope of that line. So again, if you were, one other way that this might be represented is maybe if you're given a table of values and you're asked to find the change of rate or the average rate of change between 2 values. It's this exact same thing. It's just plug and chug. Let's see, I need another paper. Where's another paper? Do I have another paper? Surely I have one somewhere. Sorry. Here we go. All right, ran out of paper. So there's that. That's the average rate of change how you can calculate it given an equation or a function, or if you're given a graph. And I didn't give an example, but also it's the same thing if you are given a table. Okay. What's next? Let's talk about something called the difference quotient. So this oftentimes comes up in college algebra, and it's kind of a little sneak peek at something that comes up a lot in calculus and gives you some sort of beforehand practice of calculating some things that you'll have to calculate in calculus, in particular derivatives. So what is the difference quotient? Well, if you're given, consider a function f, then my stomach is growling, I don't know if you heard that. The difference quotient of f, Jesus, is given by f of x plus h minus f of x over h. And that might look a little bit funky to you. This h, by the way, is just some arbitrary value, and in particular, when you get into calculus, h is going to be taken to be a very small value, a so-called infinitesimal. So that's sort of the idea, is that h it does represent just any arbitrary number, but usually it's taken to represent a really small number. And before I move forward with calculating this, I'll just point out that this is actually a really familiar difference. Or I should say, a really familiar rational expression. Because if I could write this as f of x plus h minus f of x over x plus h minus x. These are the same things, right? Because in the bottom here, x plus h minus x, the x's just cancel, and you're left with just h. Why did I write this? Because this looks very similar to, I can't pull it out now because I just hid it down under all of these pages, of course. Nope, here it is. This is similar to the rate of change formula that we just looked at, right? It's like the exact same thing, except instead of calling the values b and a, we call them x plus h and x. It's the exact same thing. So just kind of relating it, that's just to kind of relate it to what we just did. It's not like we're taking some crazy, like, veering left just, into some completely new algebra tool. This is something that we have seen. So let's calculate the difference quotient for f of x equals, and I have to be careful here because some are harder than others, let's do an x squared plus 4. We want to calculate the difference quotient for f of x equals x squared plus 4. Well, this is really, if I ask you for the difference quotient of this is actually the equivalent of me saying, what is the average rate of change of f over the interval from x to x plus h. So again, just kind of tying it back to what we already did. This is really just a new way of asking the exact same question, but we kind of have this nice formula that we can just plug things into. So, well, what do we need in order to calculate this? First, we're going to need to figure out what is f of x plus h. That means take x plus h and plug it in for x, wherever you see x. So, f of x plus h is x plus h squared plus 4. And I'm just going to kind of crunch this out. Remember, this is not big, huge asterisk. This is not x plus h squared is not x squared plus h squared. Just burn that into your head. It's not. The square doesn't get distributed. You have to FOIL this thing out. And when you FOIL it out, you're going to get that it comes out to x squared plus 2xh plus h squared plus 4. So that's f of x plus h. So now what we want to do is we want to write out all of it, f of x plus h minus f of x all over h. Okay, well, that's equal to f of x plus h, which we just found is x squared plus 2xh plus h squared plus 4. That whole thing is f of x plus h. And from that, we want to subtract f of x, which is x squared plus 4. Make sure to add in these parentheses. If you don't add in the parentheses, then you're not going to be distributing this negative, and you're going to get something wrong. All of that divided by h. There's nothing to do in the denominator yet. Just leave it as h. But watch what happens in the numerator. Well, in the numerator, I guess I'll just sort of write out this step. If I distribute this negative, then we have the first piece, x squared plus 2xh plus h squared plus 4. And then distribute this negative. It becomes minus x squared minus 4. Right? The negative gets distributed all over h. And now what? Maybe see if you can take it from here. Pause the video for half a second. See if you can finish this thing off. So what happens? We get some nice cancellation. Here's a positive x squared term. Here's a negative x squared term. They cancel. Positive 4 and negative 4 cancel. And I'm just left with 2xh plus h squared. And that's all that's left, right? 2xh. Yeah, it's h squared. Yeah, that's all that's left. Over h. And lucky us, fortunately, the numerator, every piece of the numerator has an h term. So we can factor that h out. In other words, the one h in the top cancel with each term cancels with the h in the bottom. So this h in the bottom cancels with the h of 2xh. This h in the bottom cancels with one of these h's. So it cancels out the square. So we're just left with 2x plus h. That's the difference quotient. How does this tie into calculus? If you've taken calculus or you know anything about calculus, well, take the limit of this as h goes to 0. Oops, and that gives you the derivative of the original function. So the derivative of the original function is actually just 2x. You shouldn't need to know that if you're just in college algebra right now, but just a little fun fact for you. All right, what are the other things I wanted to talk about? Behavior of graphs. Yes, let's talk about behavior of graphs now. So in particular, what does it mean for an interval of where a graph is increasing? What does it mean for an interval of the graph to be decreasing? What's it look like when it's constant? And I'll also talk really quickly about local and absolute extrema. So suppose that we have some graph and we can make it as wild as we want. Maybe something like this. Something like that. Whatever. So this is going to be in particular talking about increasing or decreasing. And increasing or decreasing means on what intervals, and this is going to sound so like stupid, you're going to be like, well, yeah, obviously. On what intervals is the graph increasing? On what intervals is the graph decreasing? So to kind of evaluate that, the way that I like to think about this is if you imagine that the graph is kind of like a roller coaster, like we're standing off to the side and we're watching like sort of like the profile of this roller coaster. And the roller coaster always moves left to right. So here's like the roller coaster cart. It's moving left to right. So when it's on this interval over here, what is it doing? Is the roller coaster cart increasing or decreasing? It's decreasing. It's going downhill on this interval until it hits about right here, where then it starts turning and it starts going uphill. Until it hits this point, and then it turns again and it starts going downhill. So here's an interval where the graph is decreasing. Here's a little interval where the graph is increasing, and then it's decreasing, and then it increases and decreases. See, it's like very, very intuitive. There's no tricks going on here with increasing and decreasing. The only thing that we need to kind of take account of is that we want to talk about the intervals where it's increasing and decreasing. So let me maybe just like put some numbers, some abstract numbers to these intervals. Let's say that this first tick mark where we go from decreasing to increasing, that's at x1. Maybe this is x2. Right here is x3. x4 corresponds to this. I didn't draw my lines very straight. We'll say this is like x5 right here, x6, something like that. All right, so let's list out the intervals where this thing is increasing. Well, from negative infinity to x1, like assuming that this graph just kind of, the behavior continues on either end. From negative infinity to x1, the graph is decreasing. From x1 to x2, the graph is increasing. So there's one interval where we're increasing, x1 to x2. From x2 to x3, decreasing. x3 to x4, increasing. So union x3 to x4. Then from x4 to x5 decreases, x5 to x6 increases. And then it's decreasing again forevermore. So where is it decreasing? Well, with this particular example, everywhere else. So we're decreasing from negative infinity to x1. Then we're decreasing from x2 to x3. Decreasing from x4 to x5. Increasing from x5 to x6, and then x6 forevermore. Beyond that, it's decreasing. So that's it. Increasing, decreasing. Sometimes graphs might be constant for just like a little bit. This would be like some sort of like a piecewise function. Like imagine that if we had something that sort of did this, maybe it like comes down, and then right here at this point, it just like gets completely flat like this, and then maybe it starts going down again. So then this graph would be decreasing from negative infinity to x1, and then from x1 to x2, it's not decreasing. Like assume that this is just a perfectly straight line that I drew. x1 to x2, it's not decreasing. It's also not increasing. It's constant. So it's constant from x1 to x2, and then beyond x2, it's decreasing again. To positive infinity. It's supposed to be a comma. It turned into like a weird, like, what is that, a sickle? Or maybe like a C if you're Greek. There we go. So increasing, decreasing, constant. Very straightforward. And these are, by the way, they're on intervals. So like if we look at this one up here, you might ask, well, like what's going on at x1? Because at x1, it's not increasing, it's not decreasing. And you might think, does that mean it's constant at x1? No. Increasing, decreasing, constant only makes sense on intervals, not at specific points, intervals. So we just don't say anything. At x1, we can't say what it's doing. It's just like a point in space. We can't say if that's like moving at all. All right, increasing, decreasing. What else do I want to talk about? Right, absolute and local extrema. So local extrema means, and when we talk about extrema, that's just a shorthand way of saying maximums and minimums. So we're looking at local maximums and local minimums. So we'll start with that first. A local maximum means that there is some interval from, and I'll write it as an inequality, we'll say like some interval a that is less than x, that is less than b, where f of x is greater than or equal to, maybe instead of an x, sorry, maybe I should say c. So f of c is greater than or equal to f of x for all, I can't write, for all x in the interval from a to b. So what does that look like in terms of a graph? Let's see here. It might be something like, let's see, maybe it comes up like this, and then goes down like this, and then does something like that. I don't know. So look at right here. Suppose that we have this interval. So they're like local maximum. Again, it's fairly intuitive. There's just some like little nuance when it comes to local and absolute maximums. Local maximums and minimums must occur on an interval. So like right here, this is sort of a maximum. This is a local maximum. It's actually an absolute maximum the way that I've drawn this as well, but it's a local maximum. Why? Because we can find this little interval, like right here. Here's our A, here's our B, and we'll say right here is that C. F of C is up here, and F of C is greater than every other value on this interval from A to B. So this is a local max. Local minimums, the exact same idea. It's just the minimums. Again, it has to occur on an interval. So if you look at like this interval right here, there's this spot right here that is less than or equal to every other value on this interval. It's a local minimum. And the thing about local minimums and maximums is that you can have a whole bunch of them. They're kind of like, it's kind of like saying, can you find some point that is a maximum on its own little tiny neighborhood? Not necessarily over everywhere forever, but on its own little tiny neighborhood. So let's look at an example where we have a couple of local extrema. And maybe this time too, I'll toss in the absolute extrema. So maybe we have a graph that doesn't continue on forever. Maybe it just sort of like starts at this point right here, and then it comes up right there, and then it comes back down just a little bit, and then it comes up here, and it comes down, and then it comes up to right here, and it stops again. So it just completely stops. And let's see here. Let's put some x values. We'll say this is x1. x2, x3, x4, x5, and x6. So maybe take a second, pause the video, see if you can list out what are all of the local maximums, what are all of the local minimums, and in particular just listing out like the x values of them because I don't have a y scale going on. So the local maximums, the local minimums, list out the absolute maximums and the absolute minimums. I haven't told you what the absolutes are, but just take a guess. Make an intuitive guess. So pause the video for however long and see if you can fill this out. Okay. So, well, local maximums, again, it's sort of like where things go from, and here's one way of thinking about local maximums and minimums. A local maximum occurs when the graph changes from increasing to decreasing, right? So right here at x2, the graph goes from increasing to decreasing. That's a local maximum. So there's a local maximum at x2. There's also a local maximum at right here, x4, another place where we go from increasing to decreasing. x4. If you wrote down that x6 was a local maximum, unfortunately, that is not wrong. Sorry, that's not right. It is wrong. Sorry. If you wrote down x6 as a local maximum, that's wrong. Yeah. They have to, local minimums and maximums must occur on an interval. This x6 is the end of an interval. So it like when I say it has to occur on an interval, you need to be able to find some x values on both sides. This doesn't have any x values to the right. So no, it's not a local maximum. It is, however, an absolute maximum. Absolute maximums and absolute minimums, unlike local extrema, there is only one of those. There's only one absolute maximum if it exists. They don't always exist. There's only one absolute minimum if it exists. They don't always exist. So just know that there's only one. It is possible for there to be some overlap. So I'll do one more example after this too. Maybe actually two quick examples, because there's another sort of strange edge case that I want to talk about. All right, where are the local minimums? Well, x1, again, not a local minimum. Has to occur on an interval. So x1, no. x3, we're going from decreasing to increasing. So x3 is a local minimum. x5 is a local minimum. What's the absolute minimum? x1. So absolute minimum or maximum, it means the minimum value that is achieved over the entire graph, everywhere, forever. Absolute maximum, it is the absolute largest value that is achieved over the entire graph, everywhere. So that's the rundown of this. Let's look at an example maybe where there's an overlap between absolute minimums and local minimums, and also a same graph where there is no absolute maximum. So let's try this graph right here. It's going to be some kind of quartic graph, like that. And just assume this thing goes off forever. And again, we'll put some points just for reference. I didn't get it going straight over the y-axis, so I need to put a point there. Yeah, there we go. All right. So, and assume too that x1 and x3, these are hitting the exact same value. Assume f of x1 equals f of x3. Okay. What are the local minimums? We'll start there. Well, x1 is a local minimum. x3 is a local minimum, because they're both occurring on intervals. How about the absolute minimum? It's actually the exact same. So a second ago I said there can only be one absolute minimum or maximum if it occurs. And what I meant by that is the value that is being achieved, not necessarily the x value. So here we have this x1 and x3, and we're assuming that the value that these hit are the same. F of x1 equals f of x3. That's the lowest point. Both of those are the absolute lowest points on this graph. So those are the absolute minimums. They also happen to be the local minimums. So there can be some overlap there. All right, let's talk about local maximum. Well, that occurs at x2. There's no local maximums that are occurring over here because these just keep going off to infinity. So how about the absolute maximum? Where are those? Did you write something out for it? You shouldn't have. There are none. For something to be an absolute minimum or an absolute maximum, we have to be able to point to where that minimum or maximum is occurring. So if there were absolute maximums, I should be able to say, yes, right here is the spot, right? Like somewhere like right here is the spot where that maximum is occurring. But that's not going to be possible. So even if you thought, the absolute maximum occurs at infinity, no, we have to be able to point to a place and say, this is where it's happening. And there's no possible way to point to infinity and say, here's where infinity is on the number line. It's not possible. So absolute maximums, there are none. Right. Yeah, so that's that. Cool, and if we had actual values, we could sort of say like where the minimums and maximums are occurring. It's probably a better way to do that. So it would be like at x1 comma f of x1 and x3 comma f of x3. That's where the local minimums and maximums are, or the local minimums in this case are occurring. So giving kind of both the x and y coordinates of the minimums and maximums. All right, so that's local and absolute extrema. If you have any questions at all, let me know.